Thank you. Thanks for the invitation. Thanks, Median, for the organization. So yes, I'm Adil Salim from Microsoft Research. I'm going to talk about Proximal method for sampling. And basically, I'm going to talk about discretizations of dynamical systems and a relationship to sampling. Okay, so what is sampling? So sampling is the task of generating samples according to a target probability distribution. And this arises in machine learning in mainly two settings. So the first setting is the setting of Bayesian inference. So in Bayesian inference, what we know about the target distribution is basically the density or the log density. And with this knowledge, we want to generate samples according to the target distribution. And in the second setting where it appears is the setting of generative models. And in that setting, what you know about the target distribution is not the density, but is a bunch of samples which are already distributed according to the target. And your goal is to generate new samples according to this target. So, for instance, for the example of images, you have a bunch of, in your data set, you have some.
Yeah, sorry, we don't hear you well. I think there's, your microphone is not good.
Okay. So, okay. Is it better now?
Yeah, it seems so. Yes, can you continue talking?
Okay. So give me 1 second. I just need to do something so that I can hear you. Okay. So yes, I was saying, so in the setting of generative models, what you know about the target distribution is no, sorry, I was giving an example. So for example, you have a bunch of images which are distributed according to the target distribution, and your goal is to generate new images, so fake images, according to the distribution of like faces. Like there's an abstract distribution of our images which contains faces, and this is how you can generate fake faces. Okay, and what I want to show in this talk is how we can leverage the extensive toolbox of optimization to design and analyze sampling algorithms, because this is what we are going to do. We are going to study sampling, but from an optimization perspective. Okay, so what is our setting? So our setting is the following. We have a function that is smooth and convex. So smooth here means that the gradient of f is Lipschitz. And we want to sample from U star, whose density is proportional to exponential minus f. So we don't know the normalization constant. This is a classical setting in Bayesian statistics. And yes, so this talk is only about the Bayesian point of view. The things that I'm going to talk about can be used to study generative modeling, but in this talk, I will only concentrate on the Bayesian case. So the knowledge is basically the density of the target distribution. So in dimension 1, we can represent what we want to do here. So here is an example. We have, so in dimension 1, we have a target distribution in orange. And our goal is to have an algorithm. So for instance, here is a Langevin algorithm, but it can be another algorithm, which generates samples such that the histogram based on the samples is close to the orange curve. Okay, so in dimension 1, we can represent the situation, but of course, what we want to do is to do the same, but in dimension 1 million. Okay, and classical algorithm for this task is the Langevin-Monte Carlo algorithm. So the Langevin-Monte Carlo algorithm updates a sequence of iterates with the following rule. From xn to go to xn plus 1, one first takes a gradient descent step using the gradient of f, and then one adds a Gaussian noise scaled by square root of 2 gamma. And so it's basically a multivariate Gaussian random variable, which is independent of xn, and whose variance is 2 gamma identity. So first intuition why this would converge, why this would be a nice sampling algorithm is that, okay, so first of all, this is an Euler discretization of a stochastic differential equation called the Langevin equation, which is written dxt equal to minus the gradient of f at xt dt plus square root of 2 dBt. So this is another discretization of this SDE. And we know the behavior of this SDE, and we know in particular that xt is going to converge in distribution to the target distribution mu star, which is exponential minus f. Okay, so we hope that by discretizing, we keep this property, we keep the fact that xn is converging to exponential minus f. And unfortunately, this is not true, but we will go back to this later. For the moment, what I want to do is to study the convergence properties of this Langevin equation, which are well established in the literature. And one way to do it is to go through the theory of Wasserstein gradient flows. So what is the Wasserstein gradient flow? So first of all, I need to define what is the Wasserstein distance, which is related to optimal transport. So I guess you know, because there are several talks on optimal transport in this workshop. But okay, I denote by P over RD is the space of probability measures over RD with finite second moments. I denote by W the two Wasserstein distance. So the squared, so W squared between two measures mu and nu is defined as the infimum over all expectations of the square distance of x and y, where x is a random variable with distribution mu and y is a random variable with distribution mu. Okay, so you take the infimum over all couplings like that, and you obtain the square Wasserstein distance between mu and mu. And finally, I denote by L2 of mu the classical space of functions from RD to RD, such that the integral of the square of f with respect to mu is finite. So P of RD endowed with the metric W. So W is a metric, and when you look at P of RD and endowed with the metric W, it gives you the Wasserstein space. So the Wasserstein space is a metric space. It's a bit more than a metric space, but it's not an Euclidean space at all. Okay, but it does have some properties. In particular, it's a geodesic space, and because it's a geodesic space, we can define geodesics over this space, and we can define a notion of convexity with respect to the geodesics. So I won't define what is geodesic convexity, but basically there's a notion of convexity for functionals defined over the Wasserstein space, and there are some important functionals that arises in practice, which are geoconvex. Okay, so for instance, the entropy. So the entropy will be denoted by h in this talk, and the entropy of a measure mu is just the integral of mu of x log mu of x dx, where mu of x denotes the density of mu. Okay, if mu doesn't have a density, then the negative entropy is equal to plus infinity. So that functional is geodesically convex. The potential. So if you look at the integral of f with respect to mu, so you look at this as a function of mu, it gives you a function over the Wasserstein space, which is called the potential associated to f. And if f is convex, then that potential is going to be geoconvex. And finally, the sum of the two previous examples, so h plus ef, okay, gives you a function curvy f, which is also geoconvex because it's the sum of geoconvex functions. But it turns out that curvy f is actually related to the Kullback-Leibler divergence between the Kullback-Leibler divergence with respect to mu star, because the KL between mu and mu star is actually equal to f of mu up to an additive constant. Okay, so look at this as a function of mu. The KL of mu with respect to mu star is equal to f of mu up to an additive constant. So we have these three functionals, h, ef, and f, which is essentially the KL, that will play a role in this talk. And yeah, there's a classical property of the KL divergence, which is that the KL is always non-negative and it is equal to 0 if and only if mu is equal to mu star. And this tells you that you can view mu star, the target distribution, as the minimizer of the KL with respect to mu star. Okay, if you look at the KL as a function of its first variable, so the measure mu, then it is minimized when mu is equal to mu star, and at the minimum it's equal to 0. So in particular, since the curvy f function is equal to the KL up to an additive constant, then mu star is the minimizer of the function curvy f. So now what we are going to do to sample from mu star is to find a nice dynamics that is going to minimize f And since this dynamic is going to minimize f, it will provide sample from the minimizer of f, which is mu star. Okay, so this is basically the point of view here. And minimizing dynamics in applied math, they often relies on the notion of gradients. So as I told you, the Wasserstein space is not an Euclidean space, so the notion of gradients is not the classical notion of gradient, but still we can define gradients for some functions defined over the Wasserstein space, and I will give some examples. So first of all, the gradient of a functional f at mu will be an element of L2 of mu. So think about a Riemannian space. You have this. Think about the Wasserstein space being a Riemannian space. So you have this. We have the Wasserstein space like a Riemannian space. Each point in this space is a measure mu, and the gradient of f at mu will be an element of L2 of mu. So L2 of mu plays the role of the tangent space. Okay, you are at mu, you have the tangent space, which is basically L2 of mu, and the gradient of f at mu will be an element of the tangent space. So okay, so some concrete examples. So for the entropy, the Wasserstein gradient is the gradient of the log density, also known as the score. For the potential, the gradient of the potential is just the gradient of f, okay, the function that is inside the potential. And we have kind of a sum rule under some conditions. The gradient of the KL of the gradient of f, it's the same because they are equal up to an additive constant. So the gradient of the KL is equal to the gradient of the entropy plus the gradient of the potential. Okay, so we see again these three functionals playing a role: entropy, potential, and KL. And so once we have a gradient, we can define minimizing dynamics, and in particular, we can define a Wasserstein gradient flow, which is the analog of a classical gradient flow over RD over the Wasserstein space. Okay, so a Wasserstein gradient flow will be a curve, so a family of probability measures mu t, such that we have equality between the time derivative of mu t and the negative Wasserstein gradient of some functional f at mu t. So this gives you the Wasserstein gradient flow if you have this equality. So I define what is, I did not define, but I talked about the right-hand side, so the Wasserstein gradient of f at the point. I didn't talk about the time derivative, so the left-hand side here. I didn't define what is the time derivative of a measure mu t, but basically you can define it. It has a name, it's called the velocity field. But for this talk, I won't need it, so I need to define. But basically, that's the same as over RD. You have time derivative being equal to minus the gradient. Okay, equality between the two. Okay, so let's return to Langevin algorithm and try to understand Langevin algorithm from the perspective of Wasserstein gradient flows. Okay, so the first relationship between Langevin algorithm and Wasserstein gradient flows holds at the continuous time level. So if you look at the continuous time Langevin dynamics, so the continuous time SDE, called the Langevin equation or Langevin diffusion, then you take a solution of the Langevin SDE, you call it like x of t, and it's a random variable, and you look at the distribution of this random variable, okay, and you call it mu t. Then mu t is going to be the Wasserstein gradient flow of the functional curve f, which is essentially the KL. Okay, so the distribution of the Langevin diffusion constitutes the Wasserstein gradient flow of the KL. So that's why the Langevin diffusion will tend to minimize the KL, and that's why the Langevin minimize the KL with respect to mu star, with respect to the target, and that's why Langevin equation sends the distribution to the target mu star, and this has a precise sense, and this was well studied in the literature of optimal transport. So basically, the behavior of the Wasserstein gradient flow of KL, for instance, is the same as the behavior of a gradient flow over RD, classical gradient flow over RD. So in particular, if you know that F is a lambda strongly convex, then there will be convergence exponentially fast in terms of the distance. So for a classical gradient flow over RD, what you would have is that you will have that the gradient flow converges to the minimizer of the functional exponentially fast in squared Euclidean distance. Here is the same rate, but the squared Euclidean distance is replaced by the squared Wasserstein distance. But basically, if f is strongly convex, then you have that mu t converges to mu star exponentially fast with this rate here, exponential minus 2 lambda t, and squared Wasserstein distance. So it's really like the analog as what you would have over RD. And furthermore, over RD, you would have, if the function is just convex, okay, not strongly convex, then you would have convergence of the function values to 0 at the rate 1 over t. And here is exactly the same. Like the function values, f of mu t minus f of mu star, converges to 0 at the rate 1 over t, and the constant here is the same. So if f is just convex, and finally, if we have Log-Sobolev inequality, which is the analog over the Wasserstein space of an inequality known in optimization as Pauli-Jasevic. So it's the same as the analog over the Wasserstein space, and it's also well understood. Then you have exponential convergence in terms of the function values. Okay, so these three inequalities are like the three inequalities that you get over RD when you study gradient flows, and you get the same here for Wasserstein gradient flows, exactly the same. Now, yeah, so now I'd like to take a particular case, the case where of the Langevin equation where f is equal to 0. So in that case, the Langevin diffusion is just dxt equal to square root of 2 dbt. So basically, x of t is equal in distribution to x of 0 plus square root of 2t b1, where b1 is just a standard Gaussian vector. Okay, so this is because this is this is just by solving this Langevin equation you obtain the equality here in the solution. Okay, so for instance, if x of 0 is equal to 0, x of t is just a Gaussian random variable with a distribution with variance 2t. Okay, 2t identity. So the discussion that we had just 5 minutes ago tells us that this x of t, if I look at this distribution, will be the Wasserstein gradient flow of the KL, but where I take f equal to 0. So if you recall that the KL is potential plus entropy, when I take f equal to 0, basically it remains only the entropy. So what it tells us is that if you take this diffusion, this equation, then you obtain the Wasserstein gradient flow of the entropy. So the take-home message of this slide is just that basically a Brownian motion, a scale Brownian motion, corresponds to the Wasserstein gradient flow of the entropy. We know how to sample a Brownian motion, so basically we know how to implement in practice the Wasserstein gradient flow of the entropy. We don't know how to do it when f is not equal to 0. We don't know how to do it exactly. But if f is equal to 0, it's all about sampling random variables. So all about sampling Gaussian variables. So we know how to implement the Wasserstein gradient flow of the entropy. Okay, so now let's return to the discretization. All of this was about continuous time. So let's return to the discretization, and let's return to Langevin Monte Carlo. So as I said when I introduced Langevin Monte Carlo does not converge to the target distribution with a constant step. And there is a simple reason for that. The simple reason is that the target distribution mu star is not invariant by Langevin Monte Carlo. And we'll see this on an example. So here I take mu star, which is a standard Gaussian with mean 0 and variance 1 in dimension 1. Okay. So this means that mu star is written exponential minus f, where f is 1/2 of the square norm. Okay, 1/2 of the squared absolute value in the dimension 1. So the gradient of f is just the identity. Okay, gradient of f is just the identity. So if I run Langevin Monte Carlo for this target solution, I obtain this algorithm. Okay, xn plus 1 equal to 1 minus gamma times xn plus square root of 2 gamma bn plus 1, where bn plus 1 is just a sequence of IID Gaussian, standard Gaussian. And we see here that mu star is not invariant, because if xn has distribution the standard Gaussian, then xn plus the variance of xn plus 1 will be 1 plus gamma square. Okay, so we see that mu star is not invariant. So what it says is that mu star is is not a fixed point of Langevin Monte Carlo, and because of this, Langevin Monte Carlo does not reproduce the convergence rates of gradient descent in the sense that it does not reproduce the convergence rate of. So the convergence rate of Langevin Monte Carlo is not a discrete analog of the convergence rate of the Wasserstein gradient flow. That's my point. Okay, it goes slower. It is slower because of the fact that with a constant step, it does not converge to the target solution. So in the sampling literature, we say that Langevin Monte Carlo is biased. So this is the terminology that we use. It's biased in the sense that it does not converge with a constant step to the target. So now what I want to do is kind of try to explain why it's biased, and why and how we can fix that. So a nice interpretation that you can find in this paper, like an important paper for the field, is that Langevin is a forward flow. So what does it mean? So if I rewrite Langevin Monte Carlo iterations as follows, I introduce an intermediate variable xn plus half, which corresponds to just performing the gradient descent step using the gradient of f, and then xn plus 1 is obtained by adding some Brownian, some Gaussian noise to xn plus half. Then I look at mu n. Okay, so once again I take the dual point of view where I look, instead of looking at the random variables, I look at the distributions. So I look at mu n, the distribution of xn, and is mu n a kind of gradient descent for f? And the answer is no. And the answer is no because it's something else. So recall the splitting. So we can write f as potential plus entropy. Okay, and it turns out that Langevin is, so it's a forward flow splitting scheme for this. So what does it mean? It means that to go from mu n to mu n plus half, what did I do? I applied the deterministic map to the point xn. Okay, I applied this map, identity minus gamma gradient of f. So this means that mu n plus half is obtained from mu n by taking the image measure. Okay, because I applied deterministic map, the image measure by the map identity minus gamma gradient of f. Okay, but recall that gradient of f is just the gradient of the potential associated to f. So this corresponds to the analog of a gradient descent over the Wasserstein space. Because what I do is to take the image measure of mu n by the map identity minus gamma times the gradient of the functional of the potential functional. So this corresponds to one gradient descent step, one Wasserstein gradient descent step for the functional given by the potential. Okay, and then I obtain mu n plus half. How do I obtain mu n plus 1? So I obtain mu n plus 1 by adding some Gaussian noise. But I explained earlier that basically adding some Gaussian noise corresponds to following the Wasserstein gradient flow of the entropy for a time gamma. Here, gamma plays the role of the time. Okay, so when I add a Gaussian noise scaled by square root of 2 gamma, actually what I do is that I output the Wasserstein gradient flow of the entropy after a time gamma. Okay, so that's why I denoted this by flow gamma h, starting from mu n plus half. Okay, the distribution of xn plus half. So I obtain mu n plus 1 by adding by following the Wasserstein gradient flow of the entropy from mu n plus half. So that's why we call it a forward flow, because gradient descent sometimes in the literature of numerical analysis is called the forward discretization. So this is the forward pass, and this is the flow step. Okay, so since this is a forward flow, so this is a forward flow, and one reason why mu star is not invariant is because the forward step and the flow step, they are not kind of adjoint to each other. So this is a term that you can find in this paper. So they are not adjoint in the sense that they do not leave mu star invariant. And now, how to fix that? So
yes, I have only 5 minutes. Yeah.
Yeah, almost done. Yeah. So how to fix that? So there is one way to fix that, there's one way to fix that. So the adjoint of the forward pass here is well known actually in the literature of proximal methods in optimization, and in particular, so if you are familiar with the proximal gradient algorithm in optimization, you can use this perspective to use an analog of the proximal gradient algorithm over the Wasserstein space, and this gives you an algorithm which I call the Wasserstein proximal gradient algorithm, where we use this. This is called the JK operator, which corresponds to the proximity operator, the analog of the proximity operator over RD. Okay, so basically you replace the flow step by this step here, this weird step, and if you do that, you obtain an unbiased algorithm which leaves mu star invariance and which reproduces the convergence rate of the Wasserstein of the Wasserstein flow. The problem of this approach is that we don't know how to implement this JKO because it relies on the minimization of a problem over the Wasserstein space, and we don't know how to do that. Okay, so this is when so here what we did is that we kept the forward path, and we replaced the flow by the adjoint of the forward. What if we think the other way around? So instead we keep the flow path and we replace it by its adjoint. And so for a long time I thought that we would be able. For a long time I thought that it would be possible to implement the JKO of the entropy. And when I moved to Berkeley to attend a semester on sampling, I thought that with the colleagues there we would find a way to implement the JKO of the entropy, but actually this did not happen. But what happened instead is that we identified the adjoint of the flow, and so I will quickly go over this thing. So basically, if you keep the flow here, you can find the Markov kernel that will be the adjoint of the flow, and that will send mu_n to mu_n plus half, while keeping the algorithm in bias. So, and this Markov kernel is it's a Markov kernel. So given the point x, it gives you a distribution which is exponential minus f